Dr. M.A. Bhagaveni, Professor, Department of Electronics and Communication Engineering, College of Engineering Gindi, Anna University, Chennai. Dr. M.A. Bhagaveni graduated from Government College of Technology, Coimbatore, has completed her Masters and PhD at College of Engineering Gindi, Anna University. Her field of interest includes cognitive radio, ad hoc networks, wireless sensor networks, and wireless communication. She has completed 2 projects, one for CVRDE and the other for DST. She is the recipient of Young Scientist Award from DST. She has got 2 Best Research Paper Awards in international conferences. She has published more than 70 research papers in reputable journals and conferences. She is author of 2 books. The one is Analog and Digital Communication and the other is Cognitive Radio, an Enabler of Internet of Things.
Welcome to the UGC lecture series for BSc Honours. This session we are going to see about frequency modulation experiment. The aim of this experiment is to perform frequency modulation using IC 566 and to calculate the modulation index for various modulating voltages. To perform this experiment, you need a audio frequency generator, the IC 566, resistors, capacitors, CROs, regulated power supply, breadboard and connecting wires. The theory for frequency modulation. The frequency modulation is a process of changing the frequency of a carrier wave in accordance with the slowly varying baseband signal. The main advantage of this modulation is that it can provide better discrimination against noise. In frequency modulation, the message signal is imbibed on the frequency changes of the carrier. As the noise disturbs only the amplitude of the carrier, the message is not affected. So, this has a very good advantage of noise free transmission. That is why we go in for frequency modulation. The IC 566 is a voltage controlled oscillator circuit that provides an oscillating signal whose frequency can be adjusted by a control voltage. The voltage controlled oscillator can generate both square wave and a triangular wave. The frequency is set by an external capacitor and a resistor and then varied by an applied DC voltage. The IC 566 contains a current source to charge and discharge an external capacitor C1 at a rate set by an external resistor R1 and a modulating DC output voltage. The Schmidt trigger circuit present in the IC is used to switch the current source between charge and discharge capacitor and triangular voltage developed across the capacitor, and the square wave from the Schmidt trigger was provided as the output of the buffer amplifier. The resistance R2 and R3 combination is a voltage divider. The voltage Vc, it must be in the range of 3/4 of Vcc to Vcc. The modulating voltage must be less than 3/4 of Vcc. The frequency Fc is nothing but the free running frequency of the voltage controlled oscillator is calculated using the formula Fc equal to 2 times the Vcc minus Vc divided by R1 C1 into Vcc. For this particular experiment, we need to fix up what is Vcc. From the Vcc value, we can compute the free running frequency of the VCO. This part will be doing it in the design process. So, the final FM modulated signal is mathematically written as S of t will be equal to amplitude of the carrier AC into cos of 2 pi FCT plus beta times sin 2 pi FMT, where Fc is the carrier frequency, beta is the modulation index and Fm is the message frequency. The design process for this, for the FM modulated signal, we will just see what are the pin configurations of the IC 566 and then we have to understand what can be the values of the various resistors that are connected to the various pins. This slide shows you the IC 566, the internal circuits and the pins that are meant to, which pin corresponds to which output. The pin number 1 is a ground connection, pin number 2 it is no connection, pin number 3 will give you square wave output. This is an output of the current source. Pin number 4 will give you triangular wave output. At pin number 5 will be giving modulation input. Pin number 6 will be connecting the timing resistor. Pin number 7 will be connecting the timing capacitor. Pin number 8 is connected to the VCC. So, this is it is a 8 pin IC. At each pin we need to connect the resistors and the capacitors to obtain the free running frequency of the VCO, and then connect the modulating input voltage at pin number 5, and we can see the frequency modulated output in terms of square wave or triangular wave at pin number 3 and pin number 4. We have just seen. Now, how this 566 is used to operate as a FM modulator. You can see you can place the IC over the breadboard. After placing the IC over the breadboard, at pin number 1 it is grounded. Between pin number 7 and ground we will be connecting the capacitor C1. We will be taking output of square wave at pin number 3, triangular wave at pin number 4. Pin number 8 is connected to VCC. Here it is written as V plus, this V plus or VCC are the same. From the VCC the resistor R1 is connected to pin number 6. From the VCC the resistor R2 and R3, this is a voltage divider bias which will be connected between the VCC and pin number 5. R3 is connected between pin number 5 and the ground. In parallel to R3 we will be providing the modulating signal, that is audio frequency generator, with Vc equal to 1 volt and with Fm equal to 1 kilohertz. We can set what can be the value of Vc depending upon the threshold conditions we saw in the theory, which should be less than 3/4 of Vcc. Okay. So, the voltage across the pin number 5 is called as Vc. This point will be called as Vcc. So, this point is Vcc, this point is Vc. So, we have seen the limits for Vc to be between 3/4 of Vcc to Vcc itself. In order to have this limit, we need to adjust or keep your value of audio frequency voltage within that value. So, then only you will get your frequency modulated output. So, here the values for R2 and R3 is given. We need to compute the values for R1 and C1 in order to fix up the free running frequency of the VCO. There is another capacitor of 0.001 microfarads. It is connected between the resistor R2 and pin number 6, the resistor R2 and pin number 6. So, this completes the circuit diagram for FM modulation. The design process in order to determine what will be the values or to fix up the free running frequency of the VCO, we are going to fix up resistor R1 to be equal to 2.7 kilo ohms, capacitor as C1 to be equal to 0.001 microfarads, and VCC is said to be 12 volts. For this set of values, now we are going to see what will be the free running frequency of the VCO. So, the Vc, the voltage at pin number 5 will be nothing but the voltage divided by a value of Vcc. So, Vcc into R2 divided by R1 plus R2, Vcc into R2 divided by R2 plus R3. These are the resistor numbers which are acting as voltage divider bias between Vcc and Vc. So, substituting the values for Vcc to be equal to 12 volts, R2 to be equal to whatever value we have selected as 10k divided by R2 value 10k plus R3 value 1.5k. So, when you solve this expression, we will get the voltage V c at pin number 5 to be equal to 10.9 volts. Now, we can verify that this voltage is less than V c c. This voltage is less than V c c. So, the free running frequency F c will be equal to 2 times V c c minus V c divided by R 1 C 1 into V c c. So, 2 into V c c is 12 volts, V c is 10.9 volts divided by R 1 value is 2.7 k, C 1 value is 0.001 microfarads into V c c, that is your 12 volts. Once you substitute all these things, you will get your carrier frequency or the free running frequency of the VCO to be equal to 67.9 kilohertz. Once you have made the circuit design, you can view this across the CRO, whether you are able to get the same designed value as 67.9 kilohertz being the free running frequency of the VCO. After this, we will be providing the input modulating signal to the pin number 5. The procedure for this to conduct the experiment is as follows. First step, the circuit is connected as per the circuit diagram. So, we have taken up, we have just seen the circuit diagram where at various pins of the VCO, we have calculated the values of R 1, C 1, R 2, R 3 and then we have ringed up the circuit. After ringing up the circuit, before giving the modulating signal, we will be observing the carrier signal at pin number 3. So, we need to measure the amplitude and frequency of the carrier signal. For amplitude and frequency measurement, we just saw the design process. From the design process, we got the carrier frequency F c to be equal to 67.9 kilohertz, 67.9 kilohertz. So, after verifying the initial setup, now we are going to apply the sinusoidal modulating signal. Apply the sinusoidal modulating signal, which is of frequency 1 kilohertz and amplitude of 1, peak to peak amplitude value of 1 volt to pin number 5. After applying it, now we are going to slowly increase the amplitude of the modulating signal and measure the F max and F min at each step. So, for one particular value of the modulating voltage, what is the del f frequency deviation that is produced is observed. The F max and F min value, the minimum frequency and the maximum frequency, F max minus F min will give us del f. So, once you compute del f, you need to tabulate it in the tabular column. So, at the lab we have seen how to compute del f just by getting your frequency modulated signal and moving the cursors, we can just fix up what is del f and find out the value of del f and we can plot it up. After getting the value of del f, we will be now calculating the modulation index MF or beta. The formula for calculating modulation index beta will be del f by Fm. Del f is maximum minus minimum frequency value, Fm is the frequency value of the message signal. So, once you get the beta value, from the beta value applying the Carson's rule, we can obtain the bandwidth of this narrowband signal, which will be the bandwidth will be equal to 2 times 1 plus beta into Fm, 2 times beta plus 1 or 1 plus beta, both are the same, into Fm. Or you can also use another expression to calculate the bandwidth required for the Fm signal as 2 into del f plus fm. Tabulate in your observation table. Then you need to repeat steps 4, 5 and 6 by varying the amplitude of the modulating signal as well as frequency of the modulating signal. So, for various amplitudes you will get del f f max minus fm. When you vary the frequency of the message signal, your bandwidth changes. The fm at the denominator will change. When you vary the amplitude of the message signal, your del f changes. So, you can tabulate it with respect to variation in your message amplitude as well as variation in your message frequency. So, the observations what we are going to note down is with respect to variation in your Vm, increase your Vm and see that this message signal plus whatever we have calculated as Vc add together should not cross Vcc. So, within those limits you can change the values of Vm. For each Vm, what is the frequency deviation produced should be noted down. From the frequency deviation produced, we compute the beta, the modulation index, which will be nothing but del f divided by fm, and from the beta value we compute the bandwidth, which is 2 into 1 plus beta times fm. Like this you can take few readings. This is for observation, and then you need to draw the waveforms of FM modulated signal. So, here I have just shown you signals with 3 different amplitudes, but you can draw it separately. For this particular sine wave, the FM modulated signal will look like this particular sine wave. So, you can see here the amplitude of the sine wave is increasing, goes to the peak value, now it starts decreasing, reaches the minimummost value and once again increases. So, this is one sine wave with some amplitude, okay, peak to peak amplitude with some value. So, for this particular sine wave, when you observe your FM modulated signal, you will be just noting down that as the amplitude is increasing, the frequency also increases and then reaches the peak value at this frequency, and slowly as the amplitude decreases, the frequency starts decreasing, reaches the minimummost value at the minimummost amplitude value, and once again as the amplitude increases, the frequency increases. So, this is for one cycle. Like that you have to vary your applied voltage value, you will get another voltage signal, another peak to peak signal. For this peak to peak signal also you can draw the waveform with respect to the changes in your amplitude, the frequency of the modulated signal changes. So, like this you can observe your waveforms, tabulate the readings and get different values of modulation index beta and the bandwidth. This completes your FM modulation. So, the results for this, thus the FM circuit using IC 566 was performed and the modulation index was found. Summary of this experiment: frequency modulation is performed using IC 566. The pin configurations of the ICs are observed. It is an 8-pin IC. The free running frequency of the IC is designed and then the circuit is completed. After completing the circuit, we need to note down the free running frequency, which is nothing but Fc. Then give the modulating signal input to the pin number 5. After providing the input, you can see or observe the frequency modulated output either at pin number 3 or pin number 4. You will get either triangular waves or square waves. You can use next level of circuits to convert this triangular wave to sine waves. The input amplitude is varied and the various FM modulated signals are noted down. This is the overall summary. This is very easy to do with IC 566, which is dependable and reliably you can see the output waveforms. If not, we can just purchase an FM modulator kit. Using the kit, it is enough if you are going to provide in without giving the modulating signal. You have to just note down what is the free running frequency of VCO, that will be your FC. After noting down the free running frequency, you have to provide your input from audio frequency to the input points of the kit. Once you provide the input modulating signal, you will be seeing the output at the output pin. From the output pin, you will be noting down what is the del f. From del f, you get the values for beta. From beta, you get the value for bandwidth. That is about the summary of this FM modulation. Finally, few questions for you. What is frequency modulation? What are the advantages of FM over AM? How FM is more noise immune? Next question is, where does FM is utilized? Last question, what happens if the input signal is a square wave? You can also check up what happens if the VC, the signal given at pin number 5, is greater than VCC. So, this completes your FM modulation. Next, we start up with FM demodulation. So, herewith we come to the end of this session. Thank you.